All right, so okay, so this is the free body diagram, okay, as we mentioned earlier, and we will do the sum of the forces in the x direction is equal to 0, sum of the forces in the y direction is equal to 0. So the forces in the x direction, so this is going to be t sine of theta minus fe, or it's equal to fe, let me write it fe, and we have t cosine theta is going to be equal to mg. So if we divide 1 by 2, if we divide the two equations 1 by 2, we get the t will cancel, and we have tangent theta is going to be equal to fe, which is q squared divided by the distance squared, a squared, divided by mg. Okay, so here we have everything. We have the mass, we have the angle theta, we have the charge, and the distance. We can calculate it clearly. A over L is equal to sine of theta, so we can write A is just L sine of theta and replaced here, and we can solve for Q. Okay, so let me go to the solution to save some time. So when you solve for Q, you find that it's equal to mg tangent theta times 2a squared. The L sine theta is a squared divided by k, and you find that the charge is equal to 4.42 10 minus 8 coulomb. Okay, so this is I know we were interrupted, but this is the it's simple, basically applying Newton's laws for the case of equilibrium. Okay, any question about this problem? Clear? Okay, all right. I'm reluctant to go in the presentation mode because usually I lose my pen in the presentation mode, so I will use this mode in order to minimize the chances of losing my pen. Okay, so the next topic is we're going to be speaking about electric field. Okay, what happens when you have a charge? The charge will actually set an electric field around it. Okay, and the electric field is said to exist in the region of space around the charge, and usually we call it the source charge. So it's displayed here by the purple color. This is a charge, there is an electric field. The purple color is stronger when you get closer to the charge because the electric field is stronger. This is very similar to a planet, for example, setting a gravitational field around it. So let's assume you have a planet, Earth, for example, okay? And so it has a large mass, the mass of the Earth. So if you have a satellite like the moon, it is not very distant from Earth. So the Earth has a gravitational field. Any object that is in this gravitational field will experience a gravitational force. And remember, we said the force of gravitation in the previous lecture. We said is the gravitational constant times the mass of the Earth times the mass of the object, in this case the moon, divided by the distance squared. And this is the distance between the moon and the Earth. And let's call it r squared. Okay, same thing. A charge will set up an electric field, and the electric field, the way we experience the electric field, we bring another charge, test charge Q0, and we place it and we'll experience a force. Except it can be a force of attraction and it can be a force of repulsion. Gravitational force is always a force of attraction. But let's assume you put a positive charge here. If you bring a positive charge nearby, it will experience repulsion. So it will experience a force of repulsion. Okay, and the electric field is actually, we will see in the next slide, is pointing in the same direction as the force on a positive charge. So this is the electric field. It's a vector also. But if you place a negative charge, it will actually experience a force of attraction. So there will be a force of attraction. This is a force of attraction on a negative charge. Okay, and the electric field is actually, in the same here, is pointing away from the charge. So this field, المجال, is what we call the electric field. Okay. So let me go here. The definition, to see the effect of an electric field of a charged particle Q at a point P, we bring a positive particle Q0, this is what we call the test charge, at a point P and measure the force on it, Fe, okay, on Q0 from Q. Okay, so here we have a charge Q here. We bring a test charge Q0 close to it. Okay, it will experience a force. Okay, and so usually this has to be positive because we can see this force is a force of repulsion. This force is a repulsion, and the electric field now is pointing in the same direction as this force. In fact, we can calculate the electric field. It's a vector. The electric field is we will define the electric field as the force that is experienced by the test charge divided by the charge of the test charge. So the force E, the vector E, which is the electric field vector, is equal to the force, the electrostatic force that is experienced by the test charge divided by the charge of that test charge. Okay, this is the vector equation, and so in fact, if Q0 is positive, E and F are in the same direction, so E and F are in the same direction, But if the test charge is negative, if Q0 is negative, that means the electric field is pointing in the opposite charge of the force. So in this case, the electric field is in opposite direction of the force. So in order not to be confused, it's better to bring a positive test charge. You bring a positive test charge, put it in the field, and look at the force. Because the electric field will always be pointing in the same direction as the force that is experienced by a positive test charge. If you make a mistake and you place a negative test charge, whatever the force is, the electric field is in the opposite direction. Because this is the mathematical equation. If Q is positive, they have the same direction, but if Q is negative, they have opposite direction. The force that is the electrostatic force and the electric field. Okay, so since the magnitude of the force is given by Coulomb's law, this is Coulomb's law, this is K, Q times Q0 divided by R squared. We said K is equal to 1 over 4 pi epsilon 0. Okay, that means we can write the equation for the electric field. The electric field, the magnitude of the electric field is the magnitude of the force divided by the charge of the test charge. Okay, so if you take this equation and divide it by the test charge Q0, you end up with this equation. So it's 1 over 4 pi epsilon 0, or K. This is K Q divided by R squared. So this is the electric field. All right. So the electric field is K Q divided by R squared. If I can do very similar thing with the gravitational field. So I can say G, the gravitational vector, is equal to the gravitational constant times the mass of the Earth. We are on Earth, divided by the radius of the Earth. We are on the surface of the Earth squared. So you can. All right. So let's put the magnitude of G. Okay. So electric field is whenever you have a charge, it will create an electric field around it. Okay, and this electric field depends on what type of charge you have. Okay, so this is what we will see in the next slide. Okay, so if the charge is positive, Q is positive, the electric field, the force, if you bring a test charge close to it, it will experience a force. It's pointing away. It's a force of repulsion. Hence, the electric field is pointing in the same direction. So we can say, as a general rule, the electric field is always pointing away from a positive charge. The electric field is always pointing away from a positive charge. Now, if this charge is negative, however, now if you bring a test charge Q0 close to it, there will be a force of attraction. Negative and positive charge, they will attract each other. So this is the force of attraction. And in this case, the electric field, you can see, is in the same direction as the force, because it's a positive test charge. So the electric field is pointing towards the source. So we can say as a general rule, if the charge is positive, the electric field that it creates is pointing away from it. If the charge is negative, the electric field that it creates is pointing towards it. You have to memorize this. So the source charge is positive. Doesn't matter what the test charge is. The electric field always points away from the positive charge. And if the charge is negative, the electric field always points towards the negative charge. That's how we recognize. So this is the general rule, and that's why you have to remember it. All right. So the next principle is the superposition principle. Yes? Ooh. What is this? Oh, much better. Thank you for. Was it here like this for some time? Huh? Somebody should raise your hand because I'm looking at you. So whenever you see a problem, please don't hesitate to stop me, tell me, point to me, because I cannot see everything at the same time. I cannot be seeing you and the screen and everything at the same time. The superposition principle says, okay, what if we have a number of charges? So here, for example, we have a charge Q1, we have a charge Q2, a charge Q1, charge Q2, and a charge Q3. Okay. Remember the superposition principle of forces. We said if you have a number of charges, the force, you use the superposition, meaning you determine the force due to each of these charges, and on a test charge, and you sum of all of these forces. Same thing for the electric field. These are vectors. You determine the electric field due to each charge at that point, okay, and then you just sum the electric fields, okay. So let me illustrate this in presentation mode. It's okay. Take a chance. I will not use my pen in the presentation mode. Okay, so here we have Q1, Q2, and Q3, and we can determine, so we are interested at the electric field at point P. So we have a test charge here, Q0. It's a positive test charge in order not to get confused, okay? And so this is the net force, assuming we have determined F due, the force due to Q1, the force due to Q2, and the force due to Q3. This is the net force. So obviously the electric field, since the electric field is going to be also pointing along the direction of, so the electric field will be pointing along the direction of this net force. Or you can do the electric field due to each charge, and you sum the electric fields vectorially, and you get the net electric field. So I can, for example, I can get, I don't know, let's say this is, let's assume this is E1. Let's assume this is E2, and let's assume this is E3. I'm assuming that all of the charges are negative, but it's not necessarily the case. And you just add these vectors. In order to add vectors, you need a representation of each vector in unit vector notation. What is the X, Y, and Z component of F1, E1, E2, E3? And then you add the X components together times I, plus you add the Y components times J, plus you add the Z components times K. All right. Okay, the unit of electric field is obviously the unit of force is newtons, the unit of charge is coulomb. So the unit of electric field is, well, let me take a chance. There is a newtons per coulomb. Okay. And we will see in the future we will use a different unit that is also valid, which is volts per meter. We will do that in the future chapter. All right, so let me see if I all right, how about with a show of hands, a test charge of 3 microcoulomb at the point P, where an external electric field is directed to the right and has a magnitude of 4. So this is the test charge at point P. The external electric field is directed to the right and has a magnitude, so the electric field is has this magnitude. If the test charge is replaced, with another test charge. Instead of plus 3 microcoulombs, it's minus 3 microcoulombs. What happens to the electric field at point P? You know what? Let me do this here and show this card, and let me try to enter this. Try this if it will work. Enter this bit dot ly forward slash NAMA1 NAMA1. All right, so let me bring the questions. Did you go to this bit dot ly forward slash NA capital NAMA for Nabil Maalij NAMA1? So you can see it here. So let me write it down. So it's bit dot ly forward slash NAMA NAMA1. There is no spaces. Okay. So, and try to enter your answers there. This is a question. Try to enter your answers there. Let me launch it first. I think it's accepting answers now. Okay. It's here. It's bit.ly forward slash NAMA NAMA1. Okay. And see if you can enter the answer there. You have always only A, B, and C. Okay, let me. Some have already done your answers. I have 4 answers here already. Okay, so let's do that and make sure. All right. So I want to determine whether the electric field is unaffected, it reverses direction, it changes in a way that cannot be determined. So and take one of these A, B, C, or D. Okay. Everybody is done? I have only 6 answers. وين البقية يا جماعة؟ We want everybody, please. bit.ly forward slash NAMA1. Okay, here. This is the question. Done or not done? It's a very important question. Let me see how many answers. We have 17 answers. Just have a few more. Give you a little bit more time. A, B, or C. Okay. So, in order to proceed, let's look at the responses. Okay. So it looks like the majority are saying B, and a minority is saying E, and a very small minority is saying C. Interesting. All right. So let's look at the answer here. All right. the electric field depends on the source charge or on the test charge? It only depends on the source charge. The reason we bring a test charge is to measure the electric field. We measure the force and we determine the electric field. So the sign and the value of the test charge does not affect the electric field. It's like the gravitational field of Earth. Okay? If you bring the moon to test the gravitation force, or you take a satellite, the satellite the UAE has around the Earth, okay, it does not matter what the mass of the satellite. The gravitational field of the Earth is not going to change because the mass of the moon or the mass of the artificial satellite. Same thing for the charge. The electric field that is caused by a source charge is only dependent on the source charge. It does not depend on the test charge that you bring. So if you make it positive, negative, it doesn't matter. The electric field will be the same. Okay? So this is this clear? So let me draw this. So this is your source charge Q. Let me call it source charge. This source charge, let's assume it's positive to make things simple. Okay, it will establish an electric field. So the electric field will be pointing away from the positive charge in all directions. Okay, so now let's bring a positive test charge Q0. So let's bring a positive test charge. So bring a positive charge and let's place it here, for example. It will experience a force. It will be a repulsive force, so this is Q0, it's positive also. It will experience a force Fe. It will just indicate to us the strength of the, yes? If you have a session in main campus, you have the excuse. I'm sorry, I'm surprised that they schedule successive lectures in this campus and the other campus. So I don't want you to drive fast between lectures. And I send an email to the registrar asking them, this cannot be a good solution for the students, but we will see. Anyway, okay, so if you need to leave for a lecture, please, if you really have a lecture, you can leave. But if you don't, I want you to listen to the rest. We still have about 20 minutes left. Okay, now we bring a negative test charge. So let's take a negative test charge. Okay, so this is Q1 is negative. Okay, and we place it in the field of the electric field. So this will experience a force opposite to the electric field because there will be a force of attraction between the positive charge, which is a source charge, and the negative charge, which is a test charge. The electric field is not affected by the test charge, whether it's positive, negative, whether it's 3 microcoulombs or 10 microcoulombs. The electric field depends on the source. واضح? I hope this is clear. So, yes, the force depends on the two charges because we have, the equation says F is equal K Q0 divided by the distance squared. That's true. But the electric field, remember, the electric field is the force divided by Q0. So it's K, Q divided by R squared. It does not depend on Q0. It does not depend on the test charge. Okay? All right. So let's move to the next topic. Okay, so the next topic is particle in electric field. What happens to the particle in electric field? Obviously, if it's a charged particle, it will experience a force. Depending on what kind of charge that caused the electric field. So, I mentioned earlier that yeah, I want to make sure that I don't get back into the same problem. Okay, so, okay. Now, let's assume we have an electric field. In this case, it's a uniform electric field. This is the electric field. Okay. If you place a charge, so this electric field, this charge here is not the source of this electric field. So you have an electric field due to something else. For example, it's due to parallel plates. This is positive and negative. Then you have a uniform electric field between these two plates. If you bring a charge Q, unfortunately we called it Q, we should have called it Q0 to make sure that you do not confuse it, but let's call it Q. It will experience a force, okay? The force that it will experience is given by this equation. So Fe is equal to the charge Q times the electric field E, okay? And so since it will experience a force, it will be moving, and if this electric field is uniform, like in this situation, it's not changing, then the force is going to be a constant force. So a particle moving under a constant force, we describe it with motion with constant acceleration, because F is equal to ma. F is equal to ma. If the force is constant, the acceleration will be constant, and we can use the equations of motion with constant acceleration that we have studied in physics 121. Okay, so you can use, let me see if I can remember those equations. So let's say y is equal to y0 plus v0t plus 1/2 at squared. You can use v is equal to v0 plus at, and you can use v squared minus v0 squared is equal to a delta y. So these are the equations of motion you have studied in physics 121. Those are still valid in this case. This is motion with constant acceleration. All right, let's do a couple of examples with electric fields. Let's assume you have a water drop, okay, that has a mass of 3 × 10⁻12 kilograms, is located in the air near the ground during a stormy day. Okay, the atmospheric electric field of magnitude, so we have an electric field due to this cloud that is equal 6×10⁻³ newtons per coulomb. Okay, it points vertically downward in the vicinity of the water droplet. So let's draw. This is the water droplet. There is an electric field pointing downward. See, this is ground here. Okay, the droplet remains suspended at rest in the air. It's suspended in the air. Okay, what is the electric charge of the droplet? First of all, how can it be suspended in the air? What are the forces acting on it? Yalla shabab. The force of? Well, we have an electric field. The storm is causing electric field, and it's charged droplet. So it will experience an electrostatic force. It will experience electrostatic force. What else? What are the other forces acting on it? Gravitational force. So let's draw them. So the gravitational force is mg, and if this is suspended in air, the other force has to be in the opposite direction. It cannot be, pointing downward. So this is Fe. And we remember Fe, we said, is equal to Q times E. We had an equation that says the electrostatic force is a charge times the electric field. Okay? What do you think in this case the charge? Is it positive or negative? Negative. Why? Because the electric field and the forces are in opposite directions, so the charge has to be negative. We said if the test charge is positive, the electric field and the force are pointing in the same direction, but if the charge is negative, the electric field, the test charge, I'm speaking about the test charge, if the test charge is negative, the electric field and the force are pointing in the opposite direction. So clearly we see here the electrostatic force and the electric field are pointing in the opposite direction, so Q has to be negative. Can we determine Q? Yes, we can do the sum of the forces equal to 0, the principle of equilibrium. Sum of the forces is equal to 0, that is equilibrium. That means here we have only forces in the y direction, so let's take positive to be in the top direction. So we can say that Fe minus mg, Fe minus mg is equal to 0, or we can say just Fe, which is Qe, is equal to mg, minus mg, is equal to 0. and we can write Q in this case is just equal to mg divided by E, and obviously we have to take care of the negative sign. Okay, so Q, so this is the magnitude of Q. Okay, magnitude of Q is mg over E, and Q is a negative charge. Okay, so this is an easy problem to solve. It's just equilibrium equation. The forces, the sum of the forces is equal to 0. We just have to remember that in this case we have one equation. Simple equation is this one. The force due to the electric field is just the charge times the electric field. This is a vector equation. So if the charge is positive, they are in the same direction. The charge is negative, the two vectors are in opposite direction. So if we solve this, we find that in this case we find the charge is equal, so minus 4.9 10 to the minus 15. Okay, so here this is actually more accurate because Fe, Q, and since E is pointing in the negative direction, that's why we have a negative sign here, minus mg, and we solve for Q, it's actually minus mg divided by E, and you get it to be negative. If you get confused, determine the magnitude first, and then use your reasoning. Is this negative charge or positive charge? So once you determine the magnitude, okay, which is simple, then you use the reasoning. The electric field is pointing downward, the electric force is upward, that means the charge has to be negative. All right. Okay. So let me quickly do this example. And all right, so here we have charge Q1 and Q2 are located on the x-axis at a distance A and B from the origin as shown in the figure. Find the components of the net electric field at the point P. So this is point P here, which is at position 0, y. So this is 0 on the x-axis and y. Evaluate the electric field at point P in the special case when Q1 is equal to Q2 and A are equal to B. Okay. And finally, find the electric field due to the electric dipole when point P is at a distance y much larger than A. So let's take it one point at a time. Find the component of the net electric field at point P, which is in position. So let's find. So here, let's draw the electric field. This is a positive charge. The electric field is pointing away from it. So this is E1. Okay, and we can write E1. Okay, this is equal K times Q1 divided by the distance squared, R1 squared. And since I want to, so this is the electric field, let's assume this angle is phi here. Okay, so the angle is phi, and it's the same as this angle. So you can see that in this case, the cosine of phi is equal A divided by R1, and sine of phi is equal Y divided by R1. Okay, and okay, so I can determine here, I can multiply this. So I want to get the x component and the y component. So this is going to be times cosine phi times I. There is a positive component in the x direction, and there is a positive component in the y direction, plus sine of phi times j. Okay, and we have the angles. All right. Now we can do the same thing for E2. This is E1. We can do the same thing for E2. Notice E2 now. The electric field is pointing towards the negative charge. The source charge is negative, so the electric field is pointing towards it. So this is the angle theta, and it happens to be the same as this angle. Okay, so we can write cosine theta is B divided by R2, and sine theta is equal to Y divided by R2. Okay, so I can do the same thing. E2 is equal K times Q2 divided by R squared, R2 squared. And so now I have to determine what are the x and the y component. This is the x component of E2. This is the y component of E2. Okay, so the x component is positive, so I can write cosine theta I. Okay, however, the y component is negative. You can see the y component of the E2 is negative. So I have to write minus sine of theta j. Okay? I can replace the values of cosines and sines because I have them. And basically, if I want to determine the net electric field, find the component of the net electric field. So E, the total electric field, is just E1 plus E2. So I can add the x components together and the y components together. So I can write E is equal k q1 divided by r1 squared cosine phi plus k q2 divided by r2 squared cosine theta. All of this times I. Okay, plus now I add the y components. So we have k q1 divided by r1 squared sine of phi. This is this component minus k q1 divided q2 sorry divided by r2 squared sine of theta j. So now I have the x and the y component of the total force. All right. So this is here. This is the x component, and this is the y component. All right. Now the next question says, evaluate the electric field at point P in the case when Q1 are equal to Q2 and A are equal to B. So this simplifies. This equation will simplify. So whenever we have Q1 and Q2, we can replace them by Q. And whenever we have so now R1 and R2 are going to be equal since A and B are equal. So R1 and R2 are equal, and the equation simplifies. So this is in order to save time. So if I replace the charge Q1 and Q2 to be by Q, and R1 squared just is equal, remember, R1 squared is A squared plus Y squared, and R2 squared is B squared plus Y squared. This is what we have done here. So now the x component simplifies to this equation, and the y component, actually the y component, they will cancel because the charges are the same, the distances R1 and R2 are the same. So because we have a negative sign, so this will cancel with this and you get 0. Okay, so now this is the equation we obtain for the electric field in the x direction. So the electric field has only the total electric field has only a component in the x direction. All right. The next question is, find the electric field due to the electric dipole when point P has a distance y much larger than A. Okay, so when the distance y much larger than A, in this case, so this is the equation. Here what we did, we replaced A divided by A, we divided, so we have cosine theta is A over R, cosine theta is A over R, okay, and R is equal to the square root of A squared plus Y squared. So we replaced here, and we have rewritten this equation. We eliminate cosine theta. So now it's equal K, Coulomb's constant, times 2 times A, the distance A. Now A and B are equal, okay, times Q divided by A squared plus Y squared to the power 3/2. Okay, since Y is much larger than A, this can be ignored in the denominator because Y is much larger, and this equation becomes, so if this is ignored because it's very small, this becomes K times 2 times A, the distance A, times Q divided by Y cubed. This equation is actually the equation for a dipole, an electric field due to a dipole. Dipole meaning negative and positive charge of the same magnitude. This is what we call a dipole, and in this case the distance between them is 2A. Okay, you're not supposed to memorize this, but it's just for completeness. All right, any questions? We're almost done. I'm falling behind relative to the schedule, so I will try to catch up. I was planning to finish this chapter today, but it's okay. We can. We had some interruptions. Any questions, please? Okay, so please make sure you check the homework. Okay, because I already posted the homework. I want something very quick, okay? Use bit.ly nama3. Huh? Okay, let me write it down. bit.ly / nama NAMA and 3. Okay, I want you to enter this. So let me go to that page myself. Were you able to access it? Let me see it. Oops. So normally you should be able to get into this page. Okay, I'm going to give you, since I have a couple of minutes, I want to test this page. Okay, so I want you to enter your ID number in front of your name. Okay, enter your ID number in front of your name and enter the number that you have seen here, 4578 in front. So here, you, for example, Halima, you enter your ID number here and you enter the number on the top. Okay, so please try to do that. Okay, and if you finish doing that, so enter your ID number. Remember, it's bit.ly / nama NAMA3 NAMA3 bit.ly / NAMA3. Okay, enter your ID number, just ID number, and enter the number on the top, which is 4578 in front of your ID number. Okay, while you're doing that, okay, I have on the column your feedback. 1 minute question. Enter what is not clear in chapter 22 so far. If you have something that's not clear, enter. Say, I'm not sure about Quran flow, I'm not sure about electric. So you can either enter it here in front of your name, and if you don't want it to be in front of your name, you can do that. You can enter it here. I'll show you. You can enter it in anonymous feedback. You see here, this is your feedback. If you want to be, and if you want to enter anonymous feedback, I just want to make sure that you are on board. So please enter. If there is something that is not clear here, if you have a question, you can enter it. If everything is clear, say points. All right? I'm going to use this often. This is what we call the 1 minute question. At the end of the lecture, I will ask you 1 minute question. For me, this is important feedback to make sure that if you have something that is not clear, I can get it, and next time I can speak about it. Okay? So, sorry for taking a little bit longer, and try to finish this. I will stop the recording. Hopefully it has recorded. Sure.